Sa barangay Kapnayan ay mayroong mga magkakaibigan na naninirahan.
Push. Oh, oh. Ayan na, matatalo na. Ano ba naman yan, no?
Ngayon pa nang namatay yung kuryente kung kailan madami akong ginagawa. Tawagan ko na nga lang yung mga friends ko. Tanungin ko rin kung wala silang kuryente.
Ano ba yan, no? Wrong timing naman, no? Kung kailan ng init-init, saka naman magwa-brown out. Wala di ba kuryente dyan? Paano naman yan? Daing
Wala
bagay.
na
Wala
eh.
na, init dito
Yung
sa amin.
flashlight na lang
Init
ako.
nga eh. Tingnan mo, oh, di kandila ako. Lakas ng kandila ko.
Lakas ng flashlight ko.
Napanood
Buti
niyo
na
ba
lang
yun
may
sa
load ako.
TikTok?
Ano yun?
Ano?
Ano
yun?
sa TikTok?
Yung experiment about sa kandila tsaka tubig. What
Ay,
if
oo,
try
Hindi
din
na lalabas yan
natin?
sa
Ayun,
FYP
trending.
ko.
Paano
Oo.
ko sa FYP ko?
At boring eh. Para hindi ubos oras.
Oo, pwede
Agree.
din.
Gawin
Sige.
natin.
Pwede rin natin gawin
Oo.
ano ba yon? Parang output pag in case nag-ano si Sir JD, ano?
Ay,
Oo,
oo.
tama.
Pwede.
Oo,
Ah,
para may
dahil
plan
mga
B.
chemist, baka mga
Ah.
chemist tayo, no?
Kaya nga eh.
Yun.
Tara, try na natin.
Tara,
Sige, B,
Tara,
tara.
tara.
try na.
Let's
Okay.
go.
The materials used for this experiment are plates with flat surface, glass, small candles, lighter or match, and a ruler to measure. While the reagents used are water, cooking oil, and dishwashing liquid. Different kinds of reagents are used to investigate the concept of viscosity. Other concepts such as the Charles law and combustion reaction were applied in this experiment, which will be also covered in more details in this video.
Paraffins, also known as alkanes, are saturated compounds with the general formula carbon N, hydrogen 2N plus 2, where N is the number of the carbon atoms. The simplest alkane is methane, or the carbon-hydrogen form, also represented by C1. Normal paraffins or N-paraffins or N-alkanes are unbranched linear molecules. Each member of these paraffins is distinguished from the immediate superior and immediately inferior member by a CH2 group known as the methylene group. They have similar physical and chemical properties which gradually change as carbon atoms are added to the chain. Oxygen forms compounds by reacting with virtually any other element, as well as by the reactions that move elements out their combination with each other. In many cases, these processes are accompanied by the release of heat and light and are then referred to as combustion.
The hydrocarbon reacts with excess oxygen during candle ignition to create carbon dioxide and water. The burning creates an air current that gives candle flames a dome shape and aids in complete combustion at the flame's bottom and outer surface. Above the flame, hot air and combustion byproducts rise. The hot gas is rising to the gas jar. As soon as it is over, the flame causes the air inside to expand, forcing some of the air out of the jar. This procedure is invisible. The burning starts in a sealed space as soon as the jar comes into contact with the water. To keep the air in the jar, press the jar into the water one more time. In the jar with more candles, water will consequently rise. The composition of the candle material will determine the kind and quantity of the products. The combustion of saturated hydrocarbons is thought to occur during burning.
In this experiment, the law of volume, or what we call the Charles law, was proved. Jacques Alexander Cesar Charles developed what is known as Charles law in 1787. According to the law, when a pressure is constant, a gas's volume and temperature are directly correlated. The formula for the law is V divided by T, where V stands for volume and T for temperature. The law is used to explain how gases behave in tires, car engines, and hot air balloons.
From the experiment, we saw how the candle went out because it ran out of oxygen. As the flame burned, oxygen was consumed. And because the candle was enclosed in a glass, the oxygen supply was depleted quickly. The candle could not continue to burn inside the glass if there was no oxygen. The candle's flame heated the air in the glass when it was still burning. Fast expanding hot air increased air pressure inside the glass more than outside. Some of the high pressure air inside leaked out from underneath the glass to regain equilibrium. You might have noticed little bubbles escaping from the glass bottom. When the candle burns out, because all of the oxygen is used up, the temperature cools quickly. This temperature decreases means that the volume also decreases, which lets the water rise to fill up that space, and this is what we call Charles' law. So Charles' law tells us that the ratio of volume to temperature must remain the same. So if one goes down, the other goes down too. This experiment's two components, which are the temperature and volume, complement one another.
The application of the concept of viscosity was also seen in this experiment. But before we dig deeper into that, first, let us define what is viscosity. Viscosity is the resistance of a fluid, liquid or gas, to a change in shape or movement of adjacent components with respect to one another. It can be thought as an internal friction between the molecules. This friction prevents the development of velocity differences within a fluid. A part of a fluid that is forced to move carries along adjacent parts to some extent. In this experiment, we have three different liquids which they are varying with their viscosities. These are the water, the cooking oil, and the dishwashing liquid. The more viscous the liquid, the more time it takes to be sipped by the glass. This means that it needs more pressure to be sipped. Among the three liquids, water was the fastest, while dishwashing liquid was the slowest, because dishwashing liquid is the most viscous among the three.